Welcome to the deep dive, where we take complex topics and try to make them clear.
Glad to be here.
Today, we're diving into some really interesting research that one of you actually sent in. It's an article called System-Wide Energy Return on Investment in a Sustainable Transition Towards Net Zero Power Systems.
That's the one.
Mm-hmm.
And this study, System-Wide Energy Return on Investment in a Sustainable Transition Towards Net Zero Power Systems, it's all about figuring out how much energy we actually get back from different ways of shifting to, well, a fully renewable power grid by 2050.
Okay.
It looks at 9 different global pathways, using a pretty new model to judge their net energy performance.
Net energy performance.
Yeah.
Okay, let's try and unpack that. What's the core question? A system-wide energy return on investment in a sustainable transition towards net zero power systems is really trying to answer.
Well, the central question is about understanding what conditions, really make these different paths to a net zero power system plausible.
Plausible how? Like technically,
Yeah,
economic.
it's more fundamental, really, from an energy perspective. It's not just if we can do it, but what's the energy cost? What kind of energy payback can we expect along the way?
Right. And the key metric they use for this is EROI, energy return on investment.
Exactly. EROI. Think of it simply as a ratio. The energy you get out of a system divided by the energy you had to invest to build it, maintain it, fuel it, everything.
So a higher EROI is better.
General, yes.
Yeah.
Much better. This study uses a, let's say, sophisticated model to calculate EROI for these future scenarios. And yes, some of the trends it finds as we switch to renewables are, well, they're quite revealing, maybe even a bit surprising.
Okay, intriguing. Now, we all know there's this big push globally, right, towards net zero. The Glasgow Climate Pact was a big moment for that.
Absolutely. And this study references that. Glasgow really highlighted, the urgent need to scale up renewables because the previous targets, the NDCs, they just weren't cutting it for keeping warming below 2 degrees Celsius.
But it's not simple.
No, far from it. As the study points out, there are huge challenges: biophysical limits, economic hurdles, political roadblocks, technology gaps. It's complex.
So how does EROI help us navigate that complexity? Where does it fit in?
It gives us a different lens. EROI isn't new, but this study specifically applies it to these global transition scenarios to see how feasible they are, especially these 100% renewable visions.
And they use an improved model.
Yes, the LUT-EROI model. The researchers argue it's better than some older methods because it tries to capture things like how different technologies work together optimally, interoperability, and the quality of the primary energy source. Things that sometimes got smoothed over in earlier ERI estimates for whole systems.
Okay, so a more nuanced picture, hopefully. Now, the study looks at 9 scenarios. Can you give us a quick flavor of what they are?
Sure. They kind of fall into 2 main buckets. First, you've got the LUT best policy scenarios, or BPS.
BPS. Got it.
These are designed to be cost-optimal ways to hit zero CO2 emissions by 2050, or even earlier in some variations. They lean really heavily on solar PV and wind.
Okay. Lots of solar and wind.
Yeah, and there are different flavors within BPS looking at like how quickly wind turbines get repowered or accelerating the whole net zero timeline to 2040, 2035, or even 2030.
Wow, 2030 is ambitious.
Very. And importantly, these BPS scenarios generally steer clear of building new nuclear plants or new fossil fuel ones, though they allow for existing gas, possibly switching to biomethane or e-methane later.
Okay, that's the BTS group. What's the other one?
The second group is what the study calls replicated reputational scenarios. Basically, they took well-known scenarios from big players like the International Energy Agency, the IEA,
Right, I've heard of their scenario.
like their STEP PES scenario, which is more business as usual, and their STS, or Sustainable Development Scenario, which involves more renewables but also keeps nuclear and includes carbon capture, CCS.
Okay, so IEA's got a couple in there.
And then there are scenarios from research by Teske and colleagues at DLR. These map out pathways for 2 degrees D and 1.5 degrees C limits, also very ambitious on renewables, but maybe factoring in different speeds and societal or political barriers.
And these ones use a wider mix of technologies.
Yeah, the IEA and TESS DLR ones often bring in more nuclear, CCS, sometimes geothermal, concentrated solar power, CSP, even wave power in some cases. So a broader tech portfolio compared to the BPS focus.
Right, that's quite a range. So after crunching the numbers with their LUT-ERY model, what did this study find? What are the big global EROI trends?
Well, maybe the most striking headline finding is that all 9 scenarios maintain an EROI above 10 right through to 2050.
Above 10. Is that good?
It's generally considered okay. The authors mention the concept of a net energy cliff, which is debated exactly where it lies, but often thought to be somewhere below an EROI of, say, 5 to 7, maybe lower for complex societies. Below that cliff, you're potentially spending almost as much energy getting energy as you're actually getting out to use.
So staying above 10 means?
It suggests all these pathways are potentially viable from a fundamental net energy standpoint. They deliver significantly more energy than they consume.
Mm.
But the trends within that vary a lot.
Okay, that's a relief, I guess. But how do the trends differ? What about those BPS scenarios, the solar and wind heavy ones?
For the BPS scenarios, the study found a pretty consistent pattern. EROI actually increases a bit initially, maybe until around 2025, as efficient renewables start displacing less efficient fossil fuels.
Okay, makes sense.
But then, as the share of renewables climbs higher and higher, and crucially, as you need to build out lots of enabling tech like batteries and other forms of storage, the EROI starts to decline steadily.
Ah, the storage penalty.
Kind of. And the study noted that the really fast transition pathways, those BPS plus scenarios aiming for 2040 or sooner, they see a sharper initial drop in EROI.
Why is that?
It seems if you have to invest a huge amount of energy upfront very quickly to build all that new infrastructure so fast, the EROI might stabilize later, but the initial hit is bigger.
Okay. What about the IEA scenarios? They kept some nuclear and gas, maybe with CCS. How did they look?
A bit different, yeah. This study shows the IEA scenarios having an initial dip, maybe 2020 to 2025, but then they actually rebound slightly. By 2050, their ERI finishes up around 19 or higher.
Higher than the BPS ones end up?
Generally, yes, according to these results. The study links this to a slower ramp-up of variable renewables, solar and wind, specifically compared to BPS. Plus, the continued contribution from nuclear and gas, sometimes with CCS, helps keep the overall ERI higher in those scenarios.
Interesting. And the TESC DLR scenarios?
They tracked fairly similar to the IEA ones until about 2040, according to the study. But after 2040, their ERI starts to trend downwards.
And the reason for that drop?
The study suggests it's linked to the significant expansion of geothermal and concentrated solar thermal power, CSP, in those scenarios post-2040. These technologies, while valuable, tend to have a higher embodied energy, meaning it takes more energy to build the plants in the first place.
Right. The study also talked about the amount of variable renewables, VRE, so wind and solar mostly, and it's linked to EROI. What was the connection there?
Yeah, this is a really key point. They found EROI tends to go up initially as you add VRE, replacing fossil fuels. But once VRE gets past a certain point, around 50% share in the BPS scenarios, the system EROI starts to fall.
The 50% mark, huh?
Around there, yeah. And the decline gets steeper as you push towards, say, 80% VRE. The main reason cited is the increasing need for energy storage to balance the grid when you rely so heavily on intermittent sources.
And storage itself affects the EROI calculation, right?
Yeah, absolutely. The study makes a useful distinction. Storage that's kind of integrated with generation, like thermal storage with CSP, or pumped hydro, can actually increase the EROI of that specific part of the system.
Okay.
But the complementary storage needed for the whole grid, think big batteries, hydrogen production and storage, synthetic methane, these tend to decrease the overall system EROI because they consume energy in their operation cycles.
This study also connected EROI to electricity costs, the LCOE, and emissions. What was the relationship they found?
This was fascinating. They found that solutions with a lower LCOE levelized cost of electricity, basically cheaper power, often correlated with a lower EROI in these future scenarios.
Wait, cheaper power means lower energy return. That seems counterintuitive.
It does at first glance, but think about it. Moving to renewables dramatically cuts fuel costs and CO2 emission costs, bringing down the LCOE. But you're investing heavily in manufacturing and deploying the renewable tech itself, plus all the storage and grid upgrades. That upfront energy investment eventually pulls the EROI down, even as the dollar cost per kilowatt hour falls.
So there's a trade-off there.
Exactly what the study highlights. You see this tension. Scenarios that maintain a higher EROI, like some IEA ones, often do so by relying more on fossil fuels, sometimes with CCS, and consequently have higher CO2 emissions, failing to hit net zero by 2050.
All the ones hitting net zero
Tend to have that declining ERI trend, especially the BPS ones, heavily reliant on VRE and storage. It really drives home that we need to look at multiple criteria: cost, emissions, and net energy when planning the transition. It's not a simple optimization problem.
Right. The study also did a sensitivity check, didn't it? Looking at the energy needed to get fossil fuels in the first place.
Yes, that was important. They looked at the embodied energy of natural gas and oil extraction and processing. How much energy does it take just to get the fuel? Because estimates for this can vary.
And did it matter much?
It mattered significantly for the IEA scenarios. which, still use substantial amounts of gas. The study found that if the actual energy cost of extracting gas is higher than their baseline assumption, the EROI for those IEA pathways could drop quite a bit more than projected.
But less impact on the renewable heavy scenarios.
Much less impact on the BPS scenarios as they phase out fossil fuels almost entirely. Their EROI is driven more by the manufacturing energy of renewables and storage, not the ongoing energy costs of fuel extraction.
Okay. And one more layer of complexity. The study mentioned global averages hide regional differences.
Hugely important point. Energy resources aren't spread evenly, obviously, so the EROI trends look different depending on where you are.
Can you give an example?
Sure. In those fast BPS plus transitions, the EROI drop was found to be much sharper in regions like Eurasia, Northeast Asia, Sub-Saharan Africa, and North America, compared to places like Europe, Southeast Asia, or South America.
Why the difference?
Often down to the mix of resources and the resulting storage needs. South America, for instance, has a lot of hydropower, which is dispatchable and has a good EROI, helping buffer the system EROI as variable renewables increase. Regions relying more heavily on just solar and wind might need more costly storage, pulling their EROI down faster.
Makes sense.
Even in the IEA scenarios, the regional EROI varies depending on what technology mix they use to replace coal in that specific region.
And there was that surprising finding about carbon capture, CCS.
Yeah, in Northeast Asia specifically, the modeling suggested that adding CCS to fossil fuel plants could actually increase the total embodied energy enough to lower the regional EROI, which is definitely something to consider when evaluating CCS deployment.
Wow. Okay, so let's try to pull this all together. After this deep dive into system-wide energy return on investment in a sustainable transition towards net zero power systems, what are the main takeaways for us?
Okay, I think there are a few key things. First, the transition to renewables, while absolutely crucial, generally leads to lower system-wide EROI compared to the fossil fuel systems we started with, especially once high VRE penetration is reached.
Right, that declining trend.
Second, the need for massive amounts of energy storage at those high VRE levels is a primary driver of that ERI decline. That's a major factor.
Okay.
Third, and this is the positive spin, all the pathways they looked at stayed above that net energy cliff. So the transition appears physically feasible from an energy in versus energy out perspective. We're not heading towards an energy deficit.
That's good news.
Fourth, there's a clear trade-off. Scenarios hitting net zero fast often have lower EROI. Scenarios maintaining higher EROI often don't get to net zero by 2050 because they keep using fossil fuels.
The multi-criteria problem again.
Exactly. Which leads to the final point. Careful planning is essential. We need to be smart about the mix of technologies we choose region by region, considering cost, emissions, and these net energy implications highlighted by the study.
So the core insight from our deep dive into system-wide energy return on investment in a sustainable transition towards net zero power systems is really that while, yes, we should probably expect a lower energy return on investment overall as we shift to a net zero system powered mainly by renewables.
The pathways looked at here still seem to deliver a solid net energy gain. They are energetically viable.
Yeah. And this analysis from system-wide energy return on investment in a sustainable transition towards net zero power systems really underlines the complexities, doesn't it? It shows why just looking at, say, cost per kilowatt hour or just emissions isn't enough. EROI adds another vital dimension.
Absolutely. It's a critical piece of the puzzle for understanding the sustainability and resilience of our future energy systems.
Hopefully this gives you, our listener, a richer understanding when you hear debates about energy policy and climate action, drawing on this look at system-wide energy return on investment and a sustainable transition towards net zero power systems. It definitely leaves us with things to think about.
For sure.
Like, is a lower EROI an acceptable price to pay for hitting net zero and achieving climate stability? And how do we best balance the different technologies, solar, wind, storage, maybe hydro, geothermal, nuclear, in different parts of the world?
These are exactly the conversations this kind of research should spark. And as always, if you come across other studies or complex topics you'd like us to tackle here on the Deep Dive, please do send them our way.
We'd love to see them. We're committed to providing these clear, hopefully insightful, and engaging analyses for you. Okay, and once again, the full title of the fascinating study we explored today was System-Wide Energy Return on Investment in a Sustainable Transition Towards Net Zero Power Systems. Until the next deep dive, keep exploring.